This video is for section 6-8, using graphs with quadratic functions. From the graph of a quadratic function, you can determine the roots of this equation. So notice the connection between the equation that has the letter y and this equation where the letter y is replaced by 0. The roots, or another name for roots, is solutions of this equation, are the x-intercepts of the graph of the function. Let's try an example. Solve this quadratic equation if we know what the graph of this quadratic equation looks like. The solutions are the x-intercepts at -1 and at +3. So the answers for this equation are x equal -1 or +3. We could verify that by solving that equation using one of the methods we know, such as factoring. That trinomial factors as x minus 3 times x plus 1. From the first factor, we see that x is 3. And from the second factor, we notice that x is -1. But the point of this lesson is you don't have to solve the equation with algebra methods if you have its corresponding graph. You can simply look to see where are the x-intercepts. Quadratic inequalities can be graphed using the same technique as linear inequalities, which we learned about in section 3-7. You graph a boundary line, which can be solid or dashed, and then shade a region of space. Let's try an example. Graph y is less than x squared minus x. Because it is degree 2, it's a quadratic equation. We expect there to be a parabola shape. But to find the parabola, it's helpful to have vertex form. So let's change this into vertex form. First up, figure out half of the coefficient of the x term. That's -1/2. Then square that value. -1/2 squared is +1/4. That's the number we would like to have as the constant term. So we can rewrite our statement as y is less than x squared minus x plus 1/4 minus 1/4. This is that completing the square process that we recently practiced. Then factor the trinomial. X minus 1/2 squared minus 1/4. Now we can see that the vertex point is located at 1/2, -1/4. Let's find that dot. From the origin, right 1/2 and down 1/4. About right here. Looking in front of the parentheses, the value of a is +1. So the parabola opens upwards. Let's find some dots to form the branches of the parabola. From the vertex, when x changes by 1 unit, y changes by 1 unit. So from this dot, over 1 unit takes you halfway between 1 and 2, and up 1 unit takes you to about right there. And there is a corresponding dot located here. In a quadratic equation where a is 1, when x changes by 2 units, y changes by 4 units. From the vertex, move to the right 2 units. We're in between the 2 and the 3 on the x-axis. Then go up 4 units. 1, 2, 3, and 4. There will be a corresponding dot located here. Before we draw in the boundary, we have to decide if it should be dashed or solid. Because there is no or equal to on the inequality symbol, it's a dashed line. The final step is to determine where to shade answers to the inequality. We want to locate all of the points where the y value is less than the boundary line. That would be under the boundary. So shade in everything under the boundary line. This is a fast way to show an infinite number of ordered pairs where every one of those ordered pairs has a y value that is less than the y values on the boundary line. Let's summarize the lesson. We discussed a connection between a quadratic function graph and solving a quadratic equation where the right side of the equation is the number 0. The connection is that the x-intercepts of the graph are the solutions to the equation. We also looked at graphing a quadratic inequality. Locate a boundary line and then shade below or above that line.